Hello everyone, it's me again, and today we'll continue the topic of polynomials with the third and the final lesson. Today we will try to get familiar with the polynomial multiplication and some of the most common polynomial equalities and how to identify the equality between two equal polynomials. Okay, all right, let's begin. I promise that today's lesson is very interesting and eye-catching. First, let's talk about the polynomial equality. Two polynomials are equal if and only if they have the same degree or order, and corresponding terms have equal coefficients. We will have a look at this example here. Let be given px equals x squared plus 3x minus 4 and qx equals ax squared plus bx plus c. So according to the definition, the two polynomials are equal if the degree are equal. So we know that in this case both are of degree 2 when a is different from 0. So we know that a must be not 0. And because they have the same degrees, so they can be equal to each other. And px equals qx if and only if. Now we will look at the terms, the corresponding terms, which are enclosed in the squares as shown on the figure here. And let's try to make the terms having the equal coefficients. Here on the green term we have the coefficient of 1. So the in the corresponding red term it has to have the equal coefficient, which is 1. So we know that a must be equal to 1. Similarly, move on to the 3x and bx. Because the coefficients must be equal, so we know that b is equal to 3. And finally, the constant term, negative 4 and c, they must be equal to each other. Now we know that a is 1, b is 3, and c is minus 4. And here is another example. Px equals x squared plus 6 minus ax minus c. And qx equals ax squared plus bx plus c minus 2. Again, the two polynomials are equal if and only if. Now we again compare the corresponding terms. The x squared must be equal to ax squared. In order to have that, we need to make a equal 1. So we know that a must be 1. Moving on to the second term. In the green term, we have 6 minus a, and in the red term, we have b. So the two corresponding coefficients must be equal to each other. So we know that 6 minus a is b. Okay, we'll come back to that later. And in the corresponding term, the corresponding constant term, we know that negative c must be equal to c minus 2. So now we will try to solve all the conditions to have the values of a, b, c, and d. According to the first condition, we know that a is 1, so we replace a is 1 in the second condition here. 6 minus 1 must be b, so b is 5. And in the third condition, we know that negative c is equal to c minus 2. So after some transformation, we achieve that 2 equals 2c, and that means c is 1. Can you follow that? I hope that I'm not moving so fast. Okay, we know that a is 1, b is 5, and c is 1, 2. Now we will confirm that. We'll try to replace the values of a, b, and c back to the polynomials. So px will be equal to x squared plus 5x minus 1. and qx is equal to ax squared plus bx plus c minus 2, and if we replace the abc into that, we will achieve the same polynomial. Px and qx now look exactly identical. So if a, b, and c uh, have have the values of 1, b, 1, 5, and c, so the two polynomials px and qx become equal to each other. All right. Now, I hope that you know how to solve the problems that require you to make two polynomials equal to each other. All you need to do is that write them into the standard form. I will come back a bit. You can see that before I compare it, both polynomials are in the standard form, right? And make sure that they have the same order or the same degree before we compare it. The next step is to compare every pair of corresponding terms. Make sure that they are identical to each other. The coefficients must be equal to each other. Okay, let's consider another example here. The two polynomials which don't have the standard form. Here we have px is x squared plus 3x plus minus 4, and qx is equal to x minus 1 times x plus a. So at first they look different, but in fact they can be transformed to be of the same standard form. After the simple multiplication that we have already learned in the previous lesson, we know that qx is equal to x plus x squared plus 1 minus a x and plus a. Oops, I just realized that I made some mistake in calculation this, but I changed it. Now, alright, it is fixed now. Now I have the correct calculation of qx. X squared plus a minus 1x minus a. Okay, so px and qx are equal to each other if and only if x squared plus x squared is equal to x squared. That is obvious. That is granted. And now 3x is equal to a minus 1x. So we know that 3 must be equal to a minus 1. Moving on, we have negative 4 is equal to negative a. So which means 4 is equal to a. Sorry, this red must cover the minus sign as well. Sorry for that. The red box must cover the negative sign as well. So we know that 4 is equal to a. A is equal to 4. All right. All right, we should move back a bit. So after we know that a is equal to 4, we know that um, px is equal to qx if qx is x minus 1 times x plus 4. You can confirm that? All right. I hope that now you know how to make the two polynomials equal to each other. First, you need to write it in the standard form, and then you compare the corresponding terms. All right, now in the next part, which is very interesting and fun to watch, I will introduce to you the most common equalities. They are very common and handy, which help you a lot in solving problems in the future. Okay. The first and one of the most fundamental equality is that the a plus b all squared is equal to a squared plus 2ab plus b squared. Okay, and I will show you why is that. I will show you the proof for that equality. You know that a plus b all squared is equal to a plus b times a plus b, right? A number squared is a number multiplied by itself. And after the polynomial multiplication, we know that a squared plus ab plus b a plus b squared is the result. And after we combine the like terms to get the final result, we have that it is equal to a squared plus 2ab plus b squared. So you can see that the left hand side is now equal to the right hand side. So we finish proving the equality. Oh, some communist kid showed up and he said that this method is so boring and he asks for another proof. Okay, can anyone have another way to prove it? Can anyone? Oh, I see a communist dog. Okay, so the communist dog has the proof that is more geometrical and more entertaining. So let's see how the communist dog solve this problem. Okay, take two segments representing A and B. All right, here we have two segments representing A and B. Okay, now take A plus B and we construct a square. We know that the formula for the area of the square is the side of the length, the side length of the square multiplied by itself. So the area of the square is a plus b because the side length is a plus b. Can you see that? One side is equal to a plus b. So the area must be a plus b squared. Okay, the cat is impressed. The next step is to divide the squares into parts. So we divide this square into four parts. A square of area a squared, a square of area b squared, and two rectangles of area AB. Can you can you see that? Can you see how we calculate the area of the squares and the rectangles? Okay, moving on. The area of the square is equal to sum of the parts, obviously. So the area, we take the sum of all the parts to have a squared plus ab plus b squared, and it is equal to a squared plus b 2ab plus b squared, and that means the a plus b squared is equal to a squared plus 2ab plus b squared because they both equal to the area of the big square. So the equality is proved. What do you think about this kind of method? We use the area and geometrical method to solve this instead of taking the multiplication of polynomials. Of course, you can see that this method takes more time than the previous one, but I think it is funny and it is something new, and maybe you won't apply this method in further future, but I think that you should know this and you can enjoy this because it is very entertaining to watch, and it is awesome. Okay, the communist cat asked for more proofs like this. Okay, can the communist dog show more? Okay, that's nice. The next equality is a minus b all squared equals a squared minus 2ab plus b squared. This one is more complicated, I think. Again, take A and B, and then if we move the A and B segments like that, we will create the A minus B. Because we have the A minus B in the equality, so we need to create things that represent A and A minus B. So this pink segment is A minus B. Do you all agree? Obviously. And now we're representing the A squared and B squared on the right hand side by squares. Here we have a big square representing A squared. Remember the side A in the first step. The large segment is equal to A. So the area of this square is A squared. And here is the area of the squared with the side B, and it is B squared. Yes, I knew that. So the pink square has the area of A minus B squared. Do you agree? Because the side length of that pink square is A minus B. So the area of this should be A minus B all squared. Okay. Are you still following? Can we move on? Okay. Now we have this rectangle here, which is interesting. You know that, come back a bit. The width of this rectangle is B. Can you see that? The width the width of this rectangle is B, and the length of the rectangle is A. Here is A. So the area of this is equal to A times B. Can you follow that? This is the critical point of solving this problem. I will widen it back a bit. Here the width is B and the length is A, right? So the area of this rectangle is A times B. Now we need to subtract A and B 2 times here on the right hand side. So we'll try to subtract the area, subtract this rectangle from the original big square. But in order to do that, we need more space. So the communist dog and cat are moving a bit. Okay, they will be right back. Okay, now I subtract AB from the original square. So the remaining area is A squared minus AB. So far so good. The big square is A squared, and after we remove the AB part, so the remaining part should be A squared minus AB. Okay. Remember that we still have the A minus B squared here. This square is of area A minus B squared. Now or we have only removed one AB, but we need to remove two AB here. In order to do that, we will add B plus. I will add back a a square of area B to the power of 2 here. So the area is now A squared minus AB plus B squared. I add the minus square back to the figure. You can see that this rectangle here also has the area of AB. Okay, again, come back to that. This side, the length of the rectangle is again A, and the width of the rectangle is also B. Can you see that? So the area of this rectangle here is AB as well. Can you follow? And now we'll try to remove that part from the remaining part. See that? Imagine that. When I remove that part, I will subtract 1 time AB. Can you see that? Now we have the remaining area, which is the A minus B squared. The A minus B squared as we calculated in the first place. But After removing the parts from the big square a squared, we have another way to express this area. It is equal to a squared minus ab plus b squared. Can you see that? After doing the removing, we know that the remaining area has the area of a squared minus 2ab plus b squared. And so this this square's area is calculated by two ways. The first way is a minus b squared, and the second way is that a squared minus 2ab plus b squared. You follow? I think this is a little bit complicated, so I will wide up a bit. Come back to that. Right in the beginning, okay, right in the beginning of the problem, we know that the pink area has the area of a minus b squared, right? We know that. We know already that the area of this square is a minus b squared. And after another way, we know that the area is also represented by a squared minus 2ab plus b squared. So the two sides are equal to each other. That's why a minus b squared is equal to a squared minus 2ab plus b squared. I know that this is complicated, so don't worry if you don't understand it in the first time. You can try to think about that later. That is totally normal, and it will help you a lot. Okay, feel free. Don't put much pressure on yourself. This is mesmerizing, right? And next, we will consider another proof for the equality a squared minus b squared is equal to a minus b plus a plus b. This one is simple, more simple than the previous one. So stay with me. Don't run away yet. Okay, now this time the cat knows how to prove it. We will make squares. And the dog says that is correct, obviously. If we take the a and b, then we can create the square a squared and b squared. Now we will try to subtract b squared from a squared. Now let's see. Can you see that? The pink area, when we subtract the b squared part from the a squared, now we have the pink remaining area, which is equal to a squared plus b squared. So far so good, right? That's right. So we know that the a squared minus b squared is equal to the pink area. Now the dog says that we should rearrange the pink area. You see that? We rearrange the pink area. And the cat realized that he is trying to make a rectangle. You see that? And you should notice that um the width of the top rectangle is b here. You see that? That's why the width of the small rectangle is b. You see that? And the length of the bottom rectangle is a, obviously. Now we have a big rectangle with the area is the pink area, which is unchanged. And now we calculate the width and the length of the rectangle. The width is already shown here, a minus b, and the length is a plus b. Can you see that? Now we try to calculate the pink area on the different method. the pink area is equal to the area of the rectangle, which is the length times the width, and it gives the answer a minus b times a plus b. So I hope that you can see what I'm trying to do here. I'll try to calculate the same area, which is the pink area, by two different methods. And the first method has the result of the left-hand side. The second method has the answer of the right-hand side. But the answer is unique. The pink area is unique, so both sides must represent the same thing. Both sides must represent the same area of the pink area. That's why we know that the both sides must be equal to each other. So a squared times x squared minus b squared must be equal to a minus b times a plus b, because they are both equal to the pink area. And that's how we prove it. Let's prove this. Again, I will wind the video back a bit. This figure, remember this figure. This is how the pink area is a plus b times a minus b. Now I'm going to show you why is the pink area equal to the a squared minus b squared. Remember that? This is why the pink area is equal to a squared minus b squared. So the both sides must be equal to each other because they both represent the pink area. That's it. I think that this kind of method is so elegant to learn. Alright, now comes the homework part. The first is to review the lesson, of course, and you also need to practice multiplying the polynomials. And the last but not least, because today is the Mid-Autumn Festival, so my homework is to enjoy it to the best. Okay, we have more time to learn math later, but take time to enjoy the Mid-Autumn Festival. Okay, and that's it. That is the end of the lesson today. Thank you very much. And the dog and the communist cat are very glad to join the class and hope to see you again. Okay, goodbye.